organisms. The reason was basically there were two kind of crabs, two kind of subpopulations. By just seeing the crab, you cannot identify whether it belongs to first type or the second type. But on the measurement, you could see that it basically belongs to two kind of subpopulations. And the parameters were estimated by Professor Pearson by the method of Kannur. But the estimation of the parameters by the ML is usually very difficult based on mixture models. There are several reasons for that. One is that the likelihood itself might be unknown. The other one is that the likelihood might have multiple modes. And this problem was more or less solved by the seminar paper by Webster in 1977. There is a breakthrough work. He introduced the EM algorithm, and he introduced a general method to find out the estimates or estimation of the data. Basically, in the mixture model, the observation can be considered as minimally data, just because of the reason that subgroup identity need not be known. Once you know that this number of crabs are belonging to group number 1, and the other part of the data is belonging to group number 2, then if you want to obtain the estimates of group number 1 and group number 2, then you can easily find out the estimates. Of course, using by method of moments, but using Dempster's method, you can find out these estimates. If you know the subgroup identity, then you can easily obtain it. But the problem with the mixture is that you may not be able to identify which population essentially this fellow or that unit having this particular measurement belongs. And it has not many applications in many areas. In fact, I have done some work on medicine, medical research. In fisheries, there are a lot many reports. Whenever you catch a number of fish, then it may belong to a number of subgroups. Similarly, in discriminant analysis and cluster analysis is in fact a part of it. And in latent class analysis, and in fact, essentially, I am talking about the mixture regression model that comes from economics. So later on, it got a lot many applications in other areas, and that's why nowadays it's important discussion. Even in computer science, also people are using machine learning and other kind of model was. Now, we will start with what you mean by a finite mixture model. A finite mixture model means the probability density function is like this. Fy is the convex combination of a set of probability density functions. These phi i's are known as mixing coefficients, and this probability density function can be parametric probability density functions. Also, for example, your Fy can be different normal probability. The restriction for the constants phi I, they are known as the mixing coefficients. Is that 0 less than phi I less than or equal to 1, and the sigma over I equal to 1 to phi I is equal to 1. So such a model is known as a finite mixture model. Finite in the sense that it is a mixture of finite number of probability density functions. Phi1, phi2, etc. Phi3 with the mixing coefficients phi1, phi2, etc. Now, in many situations, the component densities may have certain probability density functions. It may depend on some parameters also. In fact, one of the main problems in mixture analysis is that the number of parameters involved in the study will be very large. So, you need large sample size to analyze the data. Sometimes, even in some small studies, the number of parameters might be more than 40. So you require a large sample size to estimate. So the parameters involved are pi transpose and theta transpose. These are the mixing coefficient. I have kept pi g minus 1 here because one resistant like the sum of the coefficients, mixing coefficients. So you see essentially, and even your theta 1, theta 2, etc., theta g can be vector parameters also. Example, your fi y theta I can be a multivariate norm distribution where theta I can be mean vector mu I and dispersion sigma I. So you remember, even if in the two variable case for the two mixture, there can be a large number of parameters. Now, this is a simple example for the students to understand. Suppose that 40% of cancer patients receiving treatment number 1 have life lengths that follows a normal distribution with a mean 14 months and standard deviation sigma 1 is 4 months, and that of another type of typical treatment, and they have a mean length 165 months with standard deviation sigma 2 is equal to 4 months. So your mu1 is equal to 140 and mu2 is equal to 165. But the problem is that, you know, the patient don't know which treatment they have received, whether they have received treatment number 1 or treatment number 2. So a possible model for life length of a randomly selected patient will be of this, where this denotes the normal probability density function with the mean mu1 and the variance sigma. See the structure of this probability density function is, you know, the normal model, but the mixture of normal model. Basically, here it is a bimodal probability density function. But that need not be the situation. Instead of the mean length 140, 165, you know, if these are very close, for example, for the first treatment, if the mean life length is 145 and the second one is 150, this need not be bimodal in all situations. But remember, if these component means are distant places, like the difference between these two is somewhat larger than, let me think, you will be getting a bimodal probability. So, you know, this mixture density, this is another example in which, you know, suppose that, you know, your variances are same, then even when the mean is 155, 165, then it might be unimodal also. So there are several situations in which the mixture can be unimodal. The advantage of the mixture distribution is that you can model almost all sort of probability density functions. It allows you to model distributions having different shape, multimodal, and asymmetric, etc. These are examples. This is actually a mixture of 3 normals with mixing coefficients 1/5, 1/5, and 2/5 different means and variances. And this is actually the normal probability density function. It is actually an 8 mixture. The first mixture has a mean when you put I is equal to 0, and the variance also. And correspondingly, you know, the probability density is entirely different from normal, but still it is really. This is also another. This is known as this type of mixture probability density function can accommodate populations which is basically chaotic, in the sense that it may not be mesochaotic, but, you know, its kurtosis may be very large. And you know, you can have a different kind of shapes. That is advantage. I'm not going to discuss everything here, but, you know, this is actually a bimodal, skewed bimodal distribution. This kind of probability models you will encounter in practical situation, but for the sake of simplicity, most often we will take it as a normal model. And see This is known as a claw model. In some situations, you will have a multimodal probability density with very sharp modes or sharp peak. And in such situation also you can model it with a mixture probability distribution. Now remember, so far we discussed the mixture of probability model, mixture of normal probability density. But there are several situations in which this mixture can be discrete. For example, suppose that we are counting the number of COVID patients in a particular locality, in a particular panchayat or municipality. There are a different type of people. Some there is a small population coming from outside Kerala, inside India. Population coming outside India. So a number of subpopulations are there. And if you count the number of COVID patients, then belonging to these particular subpopulation. The subpopulation you may not be knowing, but you will be essentially getting the total number of counts. And these counts may be a mixture of number of subpopulations. So mixture of Poisson probability density functions are also very common. And see, this is an example. This is actually the graph of the probability mass function of a mixture of 3 Poisson distributions. See here, you have 3 modes in that case. For example, if you count something, if there are a number of subpopulations, but basically the count you are collecting without knowing which subpopulation the individual belongs. For modeling of count data, a single Poisson distribution will be, you need a very stringent condition like mean equal to variance. But in many situations, the data will be over this variance. The mean will be less than variance, and sometimes the mean can be greater than variance also. And in such situation, of course, this kind of mixture model is more apt. And another model is zero inflated Poisson model. In fact, you can see that there is also a mixture of 2 probability density functions. One is a degenerated distribution of 0, and the other one is your usual probability. So SIF model, that is zero inflated Poisson model, can also be treated as a mixture. And with a different component, in some situation, the mixture probably you will have a mixture probability density functions. One component can be normal, the other component can be a Laplace distribution. So you see the shape of the probability density function. You remember in the first part, the normal model will dominate, but at the end part, the Laplace model will dominate. This kind of probability density functions are also very common in many practical situations. And another area in which the mixture plays an important role is the idea of kernel density estimator. This is the formula of kernel density estimator, and you can see that this is also an n mixture. And this 1 by h k of the small y minus y by h. This is basically a probability density function with h as your scale parameter. And the observations, capital Yj's are the center. So basically what you are going to do is that you are placing component probability density functions, so Yj's as the center. And you can see that this plays a very important role in non-parametric estimation and modeling. And this is what we call the kernel density estimator. H is known as the window width. And here in this case, in our earlier situation, our phi I will be equal to 1 by h. So this is the kernel density estimate of n equal to 1000 observations sample from normal 1 1. So remember, as the sample size becomes larger and larger, this approaches to the actual population. Now, but if the sample size is small, apparently this mixture type you can observe from it. And, in that case, it need not be very nearer to the population, actual population. As the sample space n becomes larger, if it is coming from a univariate normal population like normal population, it will approach the normal. Now, there are other kind of distribution. This is a formula for a general mixture. And those people who know the Riemann-Schilse integral, this is the formula for a general mixture. This can accommodate continuous mixtures also. In fact, you can find out several non-probability density functions of mixtures. You might have heard of the negative binomial distribution. That is actually a mixture distribution with the mixing distribution as the gamma or exponential distribution. Exponential will give you the geometry. So this is actually a general problem, but you know, treating this is somewhat difficult, and there is another serious problem in the mixture modeling that is known as the identified. We don't have enough time to discuss all those things here, but you remember, basically we will concentrate on this finite mixture models. So finite mixture model is something like this, and in that case, your mixing function distribution is essentially a discrete distribution, and its probabilities are I1. Now, these are some other technical things. You know, I told you many of the distributions you can treat as mixture probability density function, and this is not our basic. I mean, the crux of the talk. So I'm skipping on those things. Yeah. So the main problem in the estimation of the mixing distribution is that it is basically an incomplete problem. For example, suppose that y1, y2, etc., yk are coming from the first population, and few observations are coming from the second population, etc. If you are sure that, then definitely you can estimate the parameters of phi yi varies. And you can see the proportion of observations coming from the subpopulation as the estimates you have given. But the problem is that, you know, essentially we don't know from which population this y is coming. If we have y1, y2, etc., yn as a sample from this population. So we have a hidden factor here that we represent by Zj, where Zij is equal to 1 or 0, according to whether the observation Yj is coming from the subpopulation I or not. If it is coming from the subpopulation I, then we will be denoting Zij is equal to 1 or 1, otherwise it is 0. And this is actually hidden variable or latent variable. And in fact, the mixture modeling is essentially belonging to the class of latent variable models, because you know this kind of unobservable factor are there. This is what we call the ill-posed problem in statistics. And you know, basically for in such situation, essentially we will be following the EM algorithm there. And you can see that if you do that Zj, then you can see that this Zj is basically following a multinomial distribution. And here, of course, you know, n factorial by 1 factorial, etc., because we have one single observation. So it is basically looks like phi1 raised to Z1, phi2 raised to Z2, etc., phi raised to Z2. Remember, when you take this Z1 case, so basically, you have a complete data structure of this particular type. But the problem is that, you know, your variable Z is basically an unobservable kind of thing, or a hidden variable. So your YC is equal to YZ. That is the complete data. And Y1, Y2, etc., Yn is the incomplete data. Now, a usual methodology in solving this problem is essentially the Bayes argument and the expectation maximization algorithm, which was introduced by the important paper by Dempster in 1974. And basically, we can find out the estimates of the parameters of mixture using expectation maximization method. Basically, we have two steps. In one step, what we are going to do is that we will compute the membership probability from the expectations. And in the next step, we will obtain the parameters of the model. And this is basically here we have explained it for the multivariate normal probability, multivariate normal probability distribution function. And once you know this membership probability, then you can obtain the estimates of the coefficients or the proportions, and you can continue that process to obtain the estimates of phi1, phi2 from phi g or phi g minus 1, and parameters of densities f1, y theta, etc. f g, y theta. So the maximum likelihood estimate, in principle, even though it is too tough to evaluate in the case of mixture, if you adopt the expectation maximization error, then you can easily carry out that. I will just come to the idea of mixture regression now. So once you know the idea of mixture model, then we will come across the kind of mixture regression model. Mixture regression means, essentially, if you have a situation in which the response variable follows mixture distribution, then many of your usual assumption regression theory will be violated. The error is not normal. Mixture. You may not have a linear relationship over the population, so most of the assumptions will be violated. And these kind of situations are very common in several areas. For example, in medical research, situations are not like, and the potential variability between patients should not be, because the response variable, for example, suppose that you are obtaining the sugar level of different patients, different age. The age group from 0 to 30, that may not be the same for the age group from 70 to 80. So what happens is that for the subpopulations, the variability between patients is very important. And so this kind of problem essentially first arised in the economics, as I told you, in 1972, but later on, its applications in medicine, physics, economics, marketing, increasingly in computer science and neural networks are everywhere. Now, mixture regression model is applicable when observations originate from various groups and the group affiliations are not known. That is essentially what we were talking about earlier. Mathematical form of a finite mixture regression model can be given as f of y given x psi, that is equal to sigma I equal to 1 to p pi I f I y given x theta I, where this pi I greater than or equal to 0 and sigma pi I is equal to 1. And here y is dependent or response variable with the conditional density f, and x is the vector independent. You see, in the normal theory, this is essentially the same. This distribution of the response variable y given x, that is normal with the mean a function of x and sigma square. Let's see the difference here. Now, pi A is the prior probability or mixing proportion of the component. Theta is the component specific parameter vector for the density Fi. And you have a number of parameters like this. Thus, the conditional distribution of the response variable y follows a finite mixture model. If Fy is a univariate normal density with the mean beta I transpose x and the variance sigma is squared, so that theta I is equal to beta I transpose. I have kept a beta I transpose to make it a column. Then the model is known as the finite normal mixture model. And this finite normal mixture model is a big area, and sometimes people are calling it as DMM. That is an important topic for people working in computer science. Gaussian mixture model. And if you have a Gaussian mixture model, then what is that? f of y given x psi, that is equal to sigma I equal to g phi a into phi of beta I transpose x sigma I square. And the regression equation becomes, what is the regression equation? The conditional expectation of this model with respect to x. And you can see the conditional, you can take the expectation inside. When you take the expectation of this one, you have to, you can take the expectation of this probability density function. You have to multiply it with this probability density function. You know, for the normal, the expectation is beta I transpose x, and you can see that in that case, this will be simply a linear combination or a convex combination of a number of regression equations. If x is equal to 1, you will be getting a mixture of Gaussians without a regression part, also known as a model-based clustering. In that case, you will be getting a model-based clustering. And for the estimation of the parameters, you remember the parameters in this particular model. These are, of course, beta coefficients. And then you have your sigma square also. And all these quantities you can evaluate using the expectation maximization algorithm. So first you want to obtain the membership probabilities corresponding to each and every observation. And once you obtain the membership probability, then you can go to the maximization process, and you can obtain the estimates of the things. So, you know, this is actually a synthetic example that I have created this. So you remember, suppose that you have, for example, to understand it in a simple way, suppose that in your college, 60% of the students are girl students, and the remaining 40% of the students are boy students. And I'm just taking the marks of the students in statistics. I don't know the sex of the student, whether they are boy or girl. So what happens is that there might be two regression existing. One regression for boys, the other one is girls. And the variation may also differ. Sigma square may be also different. And there is a package in package called mixed tools. These mixed tools can be used for generation of these synthetic data and analysis also. And if you do, I'm not going to explain all these things here, but you remember, if I generate a sample from this model, then you know it will be different. This is a scatter plot, X-ray plot. X is the mark in one subject, for example, suppose that in your +2 mark, and Y is there, statistics mark, whatever. So basically what happens is that if you fit a regression, you know, it may not be satisfactory. The correlation will be very small. The basic reason is that, you know, basically you have two kind of regression in that situation. And you can obtain that mixed tools itself to obtain the estimates of these parameters. Here in the package, you know, the mixing coefficients are represented by lambda. So this is your pi1, this is your pi2. Remember, while generating that data, it was 0.4. So our estimates, we are getting 0.39, that is quite satisfactory. Sample size is not too large. And you remember, you know, we are getting the values of the parameters also. So it is actually a simulated data. Now, the other one is an artificial data in which you don't have the linear regression, but you have a one part you have a linear regression, the other part you have a quadratic regression. And so, you know, y is equal to 5x plus epsilon for one subgroup, and y is equal to 15 plus 10x minus x squared plus epsilon for another subgroup. For example, suppose that that x be the age of the patients. Suppose that you are consider the younger and older patients, older age patients, and suppose that you are measuring their cholesterol level or other content. So for the first subgroup, you know, this is the regression. For the second subgroup, this is the regression. And basically, suppose that for the time being, you assume that we don't know from which category you are coming, or this may be the thing for the first population, and the other one is for the second population, then you can see that the mean is nothing but f of y given x is equal to 0.5 into this one plus this is your regression equation. So that is again a convex combination of this one. And you can use, this is actually a very good package. This is known as flexmix. You can use that package also to carry out the analysis. See, if you do this scatter plot, the first one is a linear kind of thing, so it will go like this. The other one is somewhat quadratic, so it will go like this. So you can see that if you fit a single equation for as the regression of y on x, then you know you may be getting an answer that is very, very small, quite unsatisfactory. But you know, if you use the mixture structure, then you can predict, you can obtain two regressions, and from that you can see in the first subpopulation what is the proportion there. In the second subpopulation, what is essentially the proportion. And, at the same time, you can estimate the parameters of these subpopulations also. And these are just a part of this one that students are interested in it, they can get it from. Then, of course, you know, there are generalizations of it, that is a mixture of generalized linear models. Basically, that will give you a situation in which we have essentially a generalized linear model that is introduced by Urban in 1972. And that generalization enabled us to obtain the Poisson regression, the logistic regression, negative binomial regression, and so on and so forth. And so there also, you know, the same type of typical problems will arise. For example, you know, if you want to obtain the number of COVID patients belonging to different subpopulations in your locality or in the panchayats, and you can see that the people belong to different categories. Perhaps, you know, people belong to the, as I told you, outside Kerala or outside India. So inside, people are residing here, you know, so many number of subpopulations. So if you want to model such kind of situations, essentially, you can use the generalized linear models in such situations. And finite mixture regression, finite generalized linear model can be obtained like this. So everywhere, essentially, you know, in the non-mixture situation, what we are assuming, the conditional probability density function of your response variable, even the experiment variables. Essentially, this has a particular density function. Its expectation is your regression, that can be a regression line or a regression function. So instead of it, you know, this is the general problem in which, you know, essentially the conditional probability density function is a mixture of conditional densities. So if you take the mean of this mixture, then, you know, of course, the mean will be a convex combination of regression equations. And if it is, particularly if it is normal, then of course these regression functions will be linear. So you'll be getting a convex combination of linear functions. But in general, if you have a generalized linear models, then also you can have a typical situation. For example, if you have a Poisson regression model or a logistic regression model, then also probably you can obtain a mixture of exponential, mixture of the logistic regression model and mixture of normal. And sister, you should tell me when I have to stop.
The time is up to 3 o'clock.
Okay, so I have 10 minutes more.
Yes, sir. Yes.
Yeah. So in all these situations, essentially, the estimation is a little bit tedious in the sense that a number of parameters may be involved in the estimation process. If it is a linear, then of course you can easily visualize it. But if it is non-linear, or if it is a mixture of generalized linear model, then the computation is too tough. But nowadays you have very good packages like mix tools and flexmix. That is a very nice package, and many other packages are also. Even bugs package also allows you to obtain estimates of the mixture models using Bayesian methodologies. So basically, if you have a general situation, that is a generalized linear model, you will have a link function for the mean. In the case of normal model, you have the identity link function. Essentially, you have the epsilon space itself. And this link function plays the crucial role in this distribution. And I will just show, because most of the people are not interested in this theory as such. So I will just show you how do we obtain these estimates from the simulated data. We assume that vector of mixing coefficients are 0.3, 0.7. And suppose that there are two kinds of coefficients. I have denoted the first one B1 naught, B1 1. And the second one is B20, B2. So there are two subpopulations. If it is, if we assume the linear one, then this is the first one is beta naught, beta 1 naught x plus beta 1 naught, beta 1 naught plus beta 1 naught x if you have only one observation. Then this is actually the code to generate data, and basically I have generated data. I have only one x here. So you can see if you do the flux mix analysis, then basically you will be getting the estimates as this particular thing. And basically, in the case of Poisson, as in the case of the COVID data, this estimation is more important. And basically, you can do it using flux mix. And those people who are interested in this particular area, you can go to see the help in flux mix that gives you the idea of how to obtain your beta coefficients and sigma square using flux mix. And this is a real example. This is an example based on data obtained to study the productivity of PhD students in biochemistry. The data is available in the package flexmix. The data contain 915 observations, academics who obtained their PhD degree in biochemistry in the year 1950s to 1960s. The productivity of the scholar was measured by counting the number of publications in scientific journals during the 3 years period ending the year after the PhD was received. The following variables were considered in this example. See, one variable is art, count of articles produced during last 3 years of PhD. Another is FEM, that is factor indicating gender of student with levels men and women. Another one is MAR, factor indicating marital status of student with levels single and married. KID 5, number of children aged 5 or younger. PhD, prestige of PhD department. Men's, count of articles produced by PhD member during last 3 years. This is the number of articles produced by the PhD supervisor. And this PhD, this is the prestige of the department, because if the department is in Harvard, then the prestige will be very high. On the other hand, if it is in another small university, then it will be smaller. And this is basically taken observation from America. So there, all these quantities can be easily obtained. This is a typical look of it. So the number of articles that they have written by the scholars after their PhD, 0. And of course, there are other elements also, their gender, whether they are married or not, the number of children having age less than or equal to 12, then the prestige of the PhD department. Then the last one is actually the output of the member, the number of publications by the member in the last 3 years. So basically, we are analyzing this data. So what we are interested, our response variable is basically the number of articles published by the students. So it is we have taken it's basically a count, but remember it's not a Poisson model. It's a mixture of probability density function, and we have computed the confidence intervals for the parameters. You remember there are a number of covariates. One is the intercept, the other one is their sex, married or not, kids, PhD, member or not. So all these quantities you can obtain using your flexmix. And basically we assume that there are 2 types of people in this group. And in that case, the usual Poisson regression will not work. So these are the parameters of the first component, and these are the parameters of the second. So this is beta 10, beta 11, beta 12, etc. And this is beta 20, beta 21, etc. So, and you can basically compare whether your proportions are getting better or not. This is what we call the root gram. A root gram is essentially a typical form of our histogram, in which we are taking this, if it is in terms of you remember, if it is probability, then if you take square root of it, then you will be getting an enlarged version. So that is what essentially these are the program of the positive probabilities after applying the Bayesian analysis to write out the estimates of the. So basically what you are getting is that our usual model, conventional model is not working well, because basically that population consists of 2 types of students. And one type of student is component number 1, component number 2. And merely seeing the number of publications of the student, you cannot identify whether the student is belonging to component number 1, group number 1, or group number 2. And these are the estimates of prior probabilities. And once you have the prior probabilities like that, you can obtain how many students are belonging to group number 1 and group number 2. And for the component number 1, you can obtain the estimates also. And you can see here how does these quantities are affecting the things. You see here you have essentially 2 positive factors out there. One is the number of publications of the mentor. If the mentor is publishing a lot, then actually that will be reflected in the number of articles produced by the student also. And similarly, whether they are married or not, if they are married, then they have kids, then you have to column. And according as this chord, then you will be getting this. You can obtain what are the values that they are significant also. And you can, as you are doing in the stepwise regression model, in the usual case, you can avoid those covariates which are not significant. And that can also be done in this particular analysis, and that is what we have done here. and ultimately, as we have done in the stepwise regression, we can obtain these things. So basically, what you are going to do here is this kind of situations when the usual regression is not working. Our immediate conclusion is that after plotting a scatter diagram, if it looks like a different form other than uh, linear form, the immediate our conclusion is that there is no regression at all, or there is no linear pattern at all among the variables. But basically, that is wrong. Most often, that is because of the number of subpopulations that exist in the general population. And that is the basic reason for getting our scatter diagram like that. So before concluding, what we should do is that we should see whether there is any pattern like the number of subpopulations are existing in the population. And with this, I think this is the right time to stop. I'm thankful to you, all of you, for the patient hearing after the lunch. Listening a lecture is very tough, but nowadays listening a online lecture is very easy after the lunch because anyway it's a nice occasion. Thank you all.
Thank you, sir. The meeting is now open for sharing. Dear participants, if you have any queries, you may ask now. Dear participants, if you have any queries, you may ask now. Hope there is no more queries. Now, I request all our distinguished participants to kindly switch on your videos. Now, I call upon Dr. Shankaran Kiki, Assistant Professor, Sri Narayana College, Nattiga, to deliver vote of thanks. Over to you, sir.
Okay, thank you, madam. Respected Dr. Sebastian, sir, and distinguished faculties and research scholars and students. It is my privilege to express a sincere gratitude to Dr. Sebastian George, sir, for delivering a wonderful top area, mixture regression models with applications. I heard his talk several times, and his presentation style also very marvelous one, because starting from very simple and simple manner, he develops that is the area into a good enthusiastic manner. So that is in the area mixture regression models. He starts from finite mixture as well as that is mixture of infinite mixture. That is the most familiar area, just like as using normal mixture, skewed unimodal distribution, Kurtic distribution, Clay distribution, Poisson mixture, and so on. Because I'm also working something related to some Poisson mixture as well as negative binomial mixture. So that is, we are facing so many problems relating to its estimation of parameters. And he expressed the concept of EM algorithm to solve the parameters or find the parameters at a certain level, because I'm also facing the problem of this global optimum or maybe local optimum, or the optimum value of parameter in the case of globally or maybe locally. It may be for research scholars. It is an interesting area, or maybe that is most important area for finding the global optimum value. And of course, that is in mixture regression case, he provided a very simple that is a problem, that simple way, that is illustrating a problem, and how that is solve this particular one in mixture regression model. Anyway, in the third day of recent innovations in statistical methods and applications, that is on behalf of the Christ College in Yalakuda Autonomous Department of Statistics and all the participants, once again, I express a sincere gratitude to sir. Thank you so much.
Thank you. Thank you.
Thank you, sir. May I now request Dr. Preeti John, Assistant Professor, Vimala College Autonomous Thrissur, to introduce our second speaker for the day. Over to you, ma'am.
Respected delegates and most valued participants, good afternoon and welcome to Day 3, Session 2 of National Webinar Series on Recent Innovations in Statistical Methods and Applications organized by Department of Statistics, Christ College Autonomous Irinjalakuda. Today's session on impact of statistics on data science, recent trends would be quite substantial because we have an eminent resource person for the day. It gives me immense pleasure to welcome our resource person, Dr. Syamla Krishnannair, a senior lecturer in the Department of Mathematical Sciences at the University of Zululand. She holds a PhD degree from Stellenbosch University, South Africa, and MSc Mathematics from the University of Kerala. Her research areas include mathematical image processing, signal processing, multi-scale analysis, climate modeling, process monitoring, and fault diagnosis and statistical quality control. We are very fortunate to have you here, and thank you, ma'am, for taking time out and being here today. I also extend a wholehearted welcome to all the participants from various institutions to this webinar series. Now, without any further ado, let me welcome Dr. Syamla Krishnannair for the webinar presentation. Ma'am, please.
Thank you. Thank you for the nice words. So, can I share the screen now?
Yeah, sure, ma'am.
It's visible, is it?
Yes, ma'am.
Yeah, it's okay.
Hello? Can
Yes,
you all
ma'am.
see? Okay, okay, good. Thank you. Yeah, no, actually, it's a general topic. My area of research is more on process monitoring and fault detection in chemical process systems. So when Dr. Davis asked me, I think it's 2 weeks ago or something, then I thought of like putting all these together, especially the trends that I'm looking for in process engineering system, like, the trends on like statistics on data science. So here, so it will be a very basic general talk. And towards the end of the talk, I'll just highlight some applications in process engineering system. So thank you for the opportunity. And I'm very happy to deliver the talk today. So here, the overview will be like the first question, what is the impact of statistics on data science? So there, I'll just look at the recent definition of data science and the role of statistics in data science. So based on the historical definition as well. Then the second point will be impact of statistics on the important steps in data science. So many people introduce different steps that can be used in data science, even from 1990. Then the second part will be integration of data. That's my area of specialization. So where the interaction of data with process manufacturing system modeling and control using data-driven and first principles models will be highlighted. But I'm not going to go deeper into all those different models, but I'll just give you an overview of those models that they are currently using and they used. And there are also a lot of developments happening in that area. So the historical overview evolved along with technology and the growth of data. Why I'm saying that? Application of statistics in the 1990s is not same as today's application. You all know that. But the fundamental goals are the same because statisticians help design data collection, analyze data appropriately, and interpret and draw conclusions from those analyses. Both statisticians provide tools and methods to find structures in the data and give deeper insight about data and quantify uncertainty. To do all these things, they use the fundamental objectives. So methods for achieving that objective have changed and expanded recent days because of the advancement of technology. In many sectors, especially engineering, health, and all other different fields. Because of the advanced step technology, we have larger dimensions of data, and the process systems and everything are very highly complicated, complex, and a lot of variables are there. So only difference is the application is changed. The application side of statistics is changed now. So if you look at in 1962, John Turkey, and he identified the 4 driving forces in the new science. Now it is the data science. So those driving forces are like the former theories of statistics. So it's a change in the viewpoint of statistics from a purely mathematical settings to exploratory settings. Then the other one is accelerating developments in computers and display devices, the challenges of more and ever larger size of data, the emphasis on quantification in an ever wider variety of disciplines. So these were the driving forces. I'm talking about in 1962. So that was they identified these are the driving forces for the new science. Now it is the data science. Now in 1991, Yaski and Froley introduced knowledge discovery in databases, called it KDD. That's another route of data science with its subtopics in data mining. KDD is a big building block for fostering interaction between different fields in identifying knowledge in data. And also KDD brings together many different approaches such as inductive learning, Bayesian statistics, optimization, fuzzy sets, all those things to knowledge discovery. So that was the another route for the data science. So that happened in 1991. Then recently, Keogh, he gave a new definition of the data science using the following formula. So from the disciplinary perspective, data science is a new interdisciplinary field that synthesizes and builds on statistics, informatics, computing, communication, sociology, and management to study data and its environment in order to transform data to insights and decisions by following data to knowledge, to wisdom thinking. So you can see how beautiful is that, because that happened in 2017. So that was the definition, the new definition gave by Keogh in here. So here the second part is the conditional on data environment thinking. That means all the mentioned sciences here, statistics, informatics, computing, communication, sociology, and management, all those sciences act on the basis of data, the environment, and so-called data to knowledge to wisdom thinking. So that's the new recent definition for the data science, definition of data science. So here in this slide, I'll be looking at the role of, what is the role of data science in statistics? So it's a ASA statement. So it's American Statistical Association statement that was highlighted by Jessica and Nicholas in 2016. So in 2015, a number of ASA leaders, American Statistical Association leaders, released a statement about the role of statistics in data science. So they said that statistics and machine learning play a central role in data science. We all know about it. Then they identified foundational data science fields. So those foundational data, they identified the 3 foundational data science fields. So those are database management, statistics and machine learning, distributed and parallel systems. So here, data science encourages greater mutually beneficial collaboration across these 3 fields. Also, it intersects with numerous disciplines and related research areas. So that was the statement given by ASA about the role of data science in statistics in 2015. Now, in the ongoing disciplinary collaborations based on that statement, even now, we can look at the examples like the health services, business analytics, smart cities, astronomy, and many other fields. We have ongoing collaborations. So in this slide, I'll be giving the statement by ASA again. What is the role of statistics in data science? So the previous one was the role of data science in statistics. This is the role of statistics in data science. So there are some points highlighted. So the first point is framing questions statistically allows researchers to leverage data resources to extract knowledge and obtain answers. So that's it's true. It's completely true. And the second one, the central idea in statistical inference, that there is a component of randomness in data, enables researchers to formulate questions in terms of underlying process and to quantify uncertainty in their research. Because of the randomness in that component, the component of randomness in the data allow the researchers to quantify uncertainty. And the third one, a statistical framework allows researchers to distinguish between causation and correlation, and thus to identify interventions that will cause changes in outcomes. So these are the first three statements, but it also, there are other three more statements. Statistics allows researchers to establish methods for prediction and estimation, to quantify their degree of certainty, and to do all of this using algorithms that exhibit predictable and reproducible behavior. So they talk more on the prediction part of the statistics. In this way, statistical methods aims to focus attention on findings that can be reproduced by other researchers with different data resources. So in other words, statistical methods allow researchers to accumulate knowledge. So this is the role of statistics in data science. So after that, in 1999, Wild and Pankuch came up with a statistical inquiry cycle. So that statistical inquiry cycle, like it's a PPDAC, it's a problem, plan, data, analysis, conclusion. So that was the cycle. The cycle is all about that. So the cycle defines the way one acts and what one thinks about during the courses of a statistical investigation. So that's what actually this was developed based on the undergraduate, the courses for undergraduate, but we can use the same basic plan wherever we want. So this is the statistical inquiry cycle. So it's a very basic cycle. So here, problem refers to the statement of the research questions, and plan refers to the planning, the procedures used to carry out the study, and data refers to the data collection process. And can you hear me? I think my internet is a bit unstable. Hello?
Yes, ma'am.
Hello? Can I switch off the video?
Hello?
Hello? Okay. Yeah. Okay, let me, because it says my connection is unstable. Yeah, it's audible. Okay. Okay, so here the cycle, so we have the statistical inquiry cycle that was developed by Wild and Pankuch in 1999. So it's a very basic cycle. So here I already said the problem refers to the statement of research questions, plan refers to the planning of procedures used to carry out the study, and data refers to the data collection process, and the analysis refers to the summaries and analysis of the data to answer the questions posed. And the last one is the conclusion, that refers to the conclusion about what has been learned. So this is the cycle. It was introduced in 1999. I think I have to, my slide is not moving. Let me. Okay. Now, this slide is, I'm going to, just to highlight few points in that cycle. It will help us to how to carry out that PPDAC. So that is the first one is for the statistical methods and theory. So when we look at statistical methods and theory, we need to understand the issues of design and bias. That's the first thing that we need to know. We also need to have a foundation in theoretical statistics principles for sound analysis. We also need to develop knowledge and gain experience in applying a variety of statistical methods. We also need to assess appropriateness of methods and to communicate results. So these are the few points that we need to remember when we apply statistical methods and theory in any investigation. So the next one is for data management and computation process. So there we need to be easily implementable with professional statistical software, if possible, and program. We also need to program in a higher level language and think algorithmically. We also need to use simulation-based statistical techniques and undertake simulation studies. We also need to manage the data and need to undertake analysis in reproducible manner. So these are the points that we need to keep in mind when we do the data management and computation. And the next one is for the statistical practice and communication. When it comes to reporting and analysis and all other things, so we need to remember some highlights. I mean, I'm just highlighting some points that we need to keep it in our mind. So we need to write clearly, speak fluently, and construct effective visual displays and compelling summaries. And we need to demonstrate ability to collaborate in teams and to organize and manage projects. We also need to incorporate ethical percepts into all aspects of theirs in basic terms to manage and other audiences. So these points are very important, even though we give any project, even to students or at any level. So we need to look at all these points very carefully when we want to take any analysis, any investigation. So the next one is that this year we need to apply statistical reasoning to domain-specific questions. So we identified those questions when we had that planning stage. And also we need to translate research questions into statistical questions, and we need to communicate results appropriate to different disciplinary audience. Because, for example, if you do any industrial project, if you go with a very high level of statistical terms and techniques and everything, sometimes it's very difficult for the industry to follow. Because I know for the chemical industries that I do work for them, I had to make it very in a way that they can understand and they can see things properly. So where I need more kind of visualization plots, a proper basic visualization plots, or maybe how to explain things in a very simple language. So that also very important. So we need to remember these points. So bringing all these together, so I gave you an historical overview and also the recent definition of data science, and then also the roles of statistics in data science and vice versa, and also looking at the PPDAC cycle. So we want to say, I'm just asking, what do statisticians bring to the table? So some points that we can summarize from that: importance of context in which the problem exists. That's one point. And another one is design and analysis of observational data, understanding of inference, multiplicity and reproducibility issues, statistical analysis cycle. That's a very basic procedure that somebody can follow. Expertise in making decisions with data, and experience in working on multidisciplinary teams. So these are the points that we can bring to the table. So the next one, I'm going to look at the different steps in data science. So that was recently introduced by Close and Cochin. So here, in the main steps in the data science are formulated from the 6 steps used in the popular CRISP-DM model. So that is a cross-industry standard process for data mining. So that was introduced by Brown in 2014. So from there, Close and Cochin made some modification. They added some other extra steps, because originally there were 6 steps and now they added, like you can see, almost eight steps there. So in those 6 steps were introduced by, Brown introduced in 2014. They were like business understanding, data preparation, modeling, evaluation, and deployment. But now these ideas became the fundamental ideas for applied statistics. But if you look at here now, these steps are introduced by Close in 2018. The first one is the data acquisition and enrichment, and data storage and access, data exploration or data mining, data analysis and modeling, business deployment of, optimization of algorithms, model validation and selection, representation and reporting of results. The last one is business deployment of results. So if you look at there, some of the blocks that I use the white text, and then another one I use the red text. So the white text here, especially data storage and access and optimization of algorithms, they are mainly covered by informatics and computer science area. And then, but whereas the business deployment of results, that is covered by business management. But if you look at other blocks, data acquisition and enrichment, data exploration, data mining, data analysis and modeling, and model validation and selection and representation and reporting of results, there is a lot of statistics involved there. So that will be my focus. I'll be explaining more on those blocks, but the rest is covered by different area. But these are the 8 steps that we can use in data science. So the first one is data acquisition and enrichment. So here, what they are saying, design of experiment is essential for a systematic generation of data when the effect of noisy factors has to be identified. We know that in any process, there are measurement noise available because we cannot avoid it. We have to find a way to filter them properly. So design of experiment is important in that case. Design of experiment begins with determining the objectives of an experiment and selecting the process variables for the study. So that also helps to select the key variables. Also look at the objectives of the study. A well-chosen experimental designs maximize the amount of information that design of experiment is very important for data. This is the schematic for a typical chemical process or any process with controlled inputs, outputs, discrete and continuous uncontrolled factors is a combination of all these things. So you can see there are noises. There are some variables that is not uncontrolled, maybe unobservable. Also, we cannot control it. But maybe most of the cases, industrial people can have inputs. They are controlled. They have target settings. But there are other factors that we cannot control. So you can see how complex is the system. So here, that's why when it comes to data acquisition and enrichment, design of experiment is we can utilize that. So we can utilize design of experiment to systematically generate new data, that is for data acquisition. So people, they can use simulation, can be used to generate new data or any other methods. Also to systematically reduce databases, some reduction methods, we can look at some, how can we reduce the database, the dimension of the database. Also, DOE can be utilized for tuning parameters of algorithm for improving data analysis methods themselves. So in other words, DOE is crucial for the reliability, validity, and replicability of our results. Now, the tool for enrichment of enrichment of database is to fill the missing data, use appropriate method. There are several methods available for missing data. Some people, they use principal component analysis or regression. There are different ways. So that we can use those tools for the enrichment purpose. The next step was, I think the third block or something, it was data exploration and data mining. So here, exploratory statistics is essential for data pre-processing, to learn about the contents of a database. So it's very important. We need to do some kind of a pre-processing to learn about the data. So data exploration is a fundamental for the proper usage of analytical methods. So that's it's a very basic, very important factor for the usage of analytical methods in data science. So the most important contribution of statistics is the notion of distribution of data. So for that, we need to have some kind of an understanding of the distribution of data points that we have. So why we need to have that understanding? Because it allows us to represent variability in the data as well as knowledge of parameters. So, it's very, very important, if possible, if you can have an understanding about, most of the methods, they have the assumed kind, they assume that it's normally distributed or something. But if we can have a proper idea about the distribution of the data, so we can understand the variability in the data very well, and also we can understand the parameters well. Distributions also enable us to choose adequate subsequent analytic models and methods. So that will also help us to choose the right models for analysis. So that's for data exploration or data mining part. So in other words, we need to look at the distribution of data for that process. In the same step, in the same block, I also said that statistical model, they come together. So once we have the exploration part done, then the statistical analysis, we select the model. So here, finding structure in the data and making predictions are the most important steps in data. So that's why we use the statistical models. So important examples of statistical data analysis methods. I'm just giving some examples that we can use. There are different, there are so many different ways. Advanced ones are there, hybrid ones are there, but some important thing that is hypothesis testing. So here, hypotheses are the natural links between underlying theory and statistics. The next one is the classification. So classification methods are basic for finding and predicting subpopulations from the data. The next one is the regression method. So regression methods are the main tool to find global and local relationship between features when the target variable is measured. Other one is the time series analysis. We all know about that. That aims at understanding and predicting temporal structures. For example, in technical application, like in engineering application, process control is the common aim of time series analysis. So that's my area of research. So that's one of the, so, even in other sectors, we can have similar, there are different ways in climate modeling, the forecasting and, all those things we can use. So again, now the next one is the statistical modeling. So here, when it comes to statistical modeling, complex interactions between two factors can be modeled by a connection in the graphs or networks. So that means we can use some graphical models or Bayesian network when we want to investigate the complex interaction between any two factors or more factors. And the main goal in the network analysis is deriving the network structure. There are procedures that we can follow when we want to apply the Bayesian networks and also the Gaussian graphical models. The other one is the stochastic differential and difference equations can represent models from natural and engineering science. So some of, most of the engineering and natural science area, people use stochastic differential and difference equations, for statistical modeling. So there, finding an approximate statistical models to solve such equations can give valuable insights for the statistical control of such processes in mechanical engineering and can build a bridge between applied science and data science. I just highlighted mechanical engineering, but we can also do the same thing for chemical engineering and even natural sciences. So that's what, it's very popular, those equations. So we can use them. When we can use them to build a bridge between applied science and data science. So the next one is local models and globalization. So I just want to say the local models and global models, because for global models, all training data are used to build predictions models by using statistical methods, and those models can be used to predict and test instances. Okay. So, but in local models, we first build a cluster model and divide the training data into several clusters based on the cluster model. Then in the prediction phase, each test instance is assigned a cluster number based on cluster models. And each test instance is predicted by the model, trained by the corresponding cluster instead of all the training data. So that's the difference between the local models and global models. So local models and globalization is also another some people, they look at in that way when it comes to statistical modeling. So they used to find the global properties of a time series, and properties of local models can be combined to more global characteristics. So for example, mixture models can be used for generalization of local models to global models. So in other words, model combination is essential for the characterization of real relationship in heterogeneous data, because we got this data, a huge size of data with dissimilar properties, not the same type of a data. Because even for in the chemical engineering, chemical process system, we say we have a multi-scale nature of the data, because events happens at different locations and different times. So we have this kind of characteristics. So for those kind of data, it will be always nice to combine maybe one or two models together. We call it hybrid modeling. Is very useful in that case. So that we can use that to get the proper to define, to extract the features from the data, or if there is a non-linear relationship between the parameters, we have to look at it in a different way as well. Okay, the next block was like model validation and model selection. Here, in cases where more than one model is proposed for prediction, statistical tests for comparing models are useful to structure the models based on the predictive power. So it's, we can use some statistical tests to compare them. So here the predictive power is typically assessed by means of so-called, the highlighted methods here. They are the resampling methods, where the distribution of power characteristics is studied by artificially varying the subpopulation used to learn the model. The next one is the perturbation experiments. So there is another possibility to evaluate the stability of different models against noise is assessed. So the meta-analysis as well as model averaging are the methods to evaluate combined models. Also then say model selection became more and more important in recent years, since the number of classification and regression models proposed in the literature increased with higher and higher speed. So it's model selection is very important, because we have we have several models available, especially in classification and regression. And then from there, and also the complexity of data or the computational, because some models take a lot of time to process it. So we have to minimize the computation speed as well. So in that way, model selection is very important for the selection of classification and regression models with increased computation speed. So that's for the model validation and model selection block. The next one is the representation and reporting. So here we talk about the visualization to interpret found structures and storing of models in an easy to update form are very important task in statistical analysis. So that's the last, it's very important task in any analysis. So data analysis deployment is decisive for obtaining interpretable results in data science. Besides visualization and adequate model storing for statistics, the main task is reporting uncertainties. That also we need to remember, because we need to report the uncertainty. Also, we need to give some idea about the review. How do we do the review? If somebody wants to reproduce this, how can we do that? So it's very important when we report the outcome of the experiment. Now, so that's all about the impact of statistics in data science. So now I'm going to look at the application side, especially in process engineering. So there is the integration of data science with dynamic system monitoring and control. And it was a study conducted by Jo Kuhn and Dong in 2020. And here they said, application of data science in engineering include data analytic, autonomous systems, energy analytics, environmental applications, economic data modeling, image sequence modeling, and other high dimensional time series data analytics. So a lot of applications of data science in engineering. And interaction of data with process manufacturing systems, modeling and control includes problems such as data reconciliation, state and disturbance estimation, differential property estimation. My area of research is in process monitoring. So all the above problems are solved by using both data-driven and first principle models with varying proportion, because these days we have like I mean, as I said earlier, because of the advancement of technology, every second or maybe every minute or thousands of data we are getting it in the process. And also the system is highly complex with a lot of variables. Sometimes you can have more than 20, 30 variables or even 50 variables in particular unit. You know, for example, if you take a flotation unit or something like that, it's quite a lot of variables are there. So it's a multivariate data. Some of the variables are controlled, some of the variables are not controlled, and also there are like noise, quite a lot of noises. So we need to be like, we need to use some kind of a data-driven, advanced data-driven, multivariate or multi-scale techniques. And also the first principles models are also very important, because especially in the engineering, process engineering system, we have to look at the knowledge and the data-driven models together, because we need to have an understanding of the process. So knowledge of that will, from the knowledge-based information, we will get a good understanding about the variables, that is, or even the process. Then beyond the top, we need to select advanced models to extract the information. So here, time series data in the process manufacturing system use dynamic latent variables. So I just said the general word of dynamic latent variable modeling methods. They use that to extract the principal dynamics in a low dimensional subspace of the data. In the early stage, people used principal component analysis and partial least squares. Then after that, they went on they modified because of the nature of the data, because they found that the data is non-linear, and the linear methods cannot extract sufficient information from the data. So they went and extended those one like a non-linear PCA. And again, then the studies came out like the multi-scale nature of the data. Then people went and developed multi-scale methods. Then now recent days, we are using artificial intelligence together with this all statistical techniques. So it's a combination, we call it hybrid model. So there are so many techniques are available. I'm just called them dynamic latent variables, but I just want to recently in 2018, came up with another one, dynamic inner PCA. It's an extension of the PCA. Also, they came up with dynamic inner canonical correlation analysis. They also come up with that. But dynamic inner PCA, they use that to maximize the covariance between the extracted data and prediction. So I normally use spectral techniques to pre-process the data. Then I use the normal linear or non-linear technique to detect the faults from the pre-processed version of the data. So dynamic latent variable methods effectively extract latent dynamic features from the data for easy interpretation, prediction, and visualization. So, each and every method has got its own advantages and limitations. So it's very important the right selection of the model for the right process, because some processes are like very complicated or very with a lot of noisy or very highly correlated variables. So we need to be very careful which model we are going to use. The emerging field of data science is a promising source of new tools or instruments to help engineers improve and optimize the operation and control of engineering system. So we already know about that. So the essence of data science in process system engineering. So here it says, specialized analytics are expected to integrate data science with established framework of systems and control practice. So the essence of data science for system engineering can be summarized as follows. So it can be like, say, prediction, interpretation, decision making. So prediction means to predict critical variables from others using predictive analytics. Interpretation, to extract features or new knowledge from data to help with visualization and diagnostic. And the last one is the decision making. So these are the essence of data science for PSC, for process system engineering. So industrial data analytics, in that, in this slide, I'll say that industrial system data require specialized analytics combined with the domain knowledge to achieve maximum. I mentioned that earlier, because we need to combine those two together. We need to have some kind of a domain knowledge. And also we need to use some specialized data analytic techniques to extract the information. So for that will help us to optimize the process or get the maximum benefit out of it. And data analytics provide real-time information that reflects changes in the process, characterizes uncertainty, and indicates emerging situation. Because in the chemical industrial data or any process, things are happening, because if you say, let's say, a degradation of the equipment, you won't be even see that in the signal. It's a very slow process. But any shift or anything happened all of a sudden, you will see a spike in the signal. So these changes are happening on a regular basis. So we need to monitor the system in such a way that we can prevent accidents as early as possible. So data analytic methods, especially the control charts and all other recent charts or plots they use now, it will allow the industry people to maintain the process or stop those incidents well in advance. So data from real-time process control and operations are typically high dimensional, because I mentioned that early. If you look at a flotation process, some plants are like, we got a lot of mining sites here. So in there, you start from the many different process, adding catalyst, and then it comes to flotation. Even the flotation unit, there are a lot of process they do. So all those, if you put those two, everything together, so we can say the operations are typically high dimensional. And the time series, high dimensional, so that means we get high dimensional time series with complex dynamics and uncertainty. So how are we going to extract information? How are we going to detect faults in such a system? So, data analytics helps. We need to use the data analytics with the domain knowledge. So for that, supervised and unsupervised dynamic latent variables models are used in the process system engineering for feature extraction, dimension reduction, visualization, and interpretation. Since the data is very huge and with a lot of variables and highly correlated, some kind of a dimension reduction is needed. So we use some certain techniques to do that. Then we need to extract the information properly. So for that, supervised and unsupervised DLV methods can be used. So in conclusion, I would like to say that the role of statistics in data science is underestimated as compared to computer science. So this is in particular for areas of data acquisition and enrichment, as well as for advanced modeling needed for prediction. Statisticians are well advised to more actively play their role in the modern and well accepted field of data science. Combining mathematical methods and computational algorithm with statistical reasoning, particularly for big data, will lead to scientific results based on suitable approaches. Finally, only a balanced interplay of all sciences involved will lead to successful solutions in data science. So that's my conclusion. Thank you.
Thank you, ma'am. Dear participants, if you have any queries, you may ask now. Dear participants, if you have any queries, you may ask now.
Hello, ma'am. Hello. Good afternoon, ma'am.
Hello. Yeah, good afternoon.
Ma'am, what's the difference between confidence level and confidence interval? These are the same. Confidence hypothesis testing, I think. Ma'am told in hypothesis testing.
Yeah, they are the different stages they use for the data mining and statistical modeling part. So confidence, in the control chart, we set the confidence limit. So for that, you look at the type 1 and type 2 errors. So we can, and we can look at those errors and decide what are the limits that we need to have. So sometimes they say 95% confidence level or 99%. So if I use that 99% or 95% confidence limit or something, then I always expect that 10%. If I use 99, I expect that 10% of data points can go out of my control chart. Is that clear?
Yes, ma'am. Yes. Okay. Okay. Confidence level in the hypothesis is a probability.
Sorry, it's again depends on your data and also the depends on the process that you are handling.
Yeah. Okay. Okay, ma'am. Thanks a lot.
Okay, thanks.
Thank you, ma'am. Any other queries? Hope there is no more queries. Now I call upon Ms. Ramya MS, Research Scholar, NMLA University, to deliver vote of thanks. Over to you, Ramya.
You may I audible, ma'am?
Yes.
Good afternoon, one and all present here. Respected crowd, this was one of the finest programs in the webinar session conducted by the Christ College Irinalakuda. The presentation on the impact of statistics on data science by Dr. Syamla Krishnannair, Madam of Mathematical Science Department of Zululand University was the most inspiring. Today, I am honored to have been offered to convey the vote of thanks to Dr. Syamla Krishnannair, Madam. Her topic was a really fascinating and a very motivating one. I'm sure that each one of us who were blessed to have heard her words have found it a really striking, unforgettable experience. I'm speechless to convey my sincere thanks towards Madam for her magnificent presentation. Yet, as part of my obligation, I express my heartfelt gratitude on the side of RISMA 2021. With this, I would like to conclude my words and I wish her all the luck in the world. Thank you.
Thank you, Ramya.
Thank you. Okay, ma'am. Thank you for the nice words.
Okay. Moving on to our last session of the day, I invite Dr. P.O. Jensen, Principal, Sahridaya College of Advanced Studies, Kodagara, to introduce our speaker. Over to you, sir.
Okay. I'm audible to you?
Yes,
yeah,
sir.
Audible.
Okay. Good afternoon, one and all. Today I'm very much happy because this seminar is, the reason for this seminar is one of my old student, Dr. Davis Anthony Mundasheri. And the talk is also made by one of my old student, Dr. S.M. Sunoj. So coming to my personal duty, Dr. S.M. Sunoj, Professor, Department of Statistics, Cochin University of Science and Technology, Cochin is presenting on today. Dr. S.M. Sunoj has teaching experience of more than 20 years, and he acquired doctorate from CUSAT itself, and his area of interest are distribution theory, reliability modeling, information measures, He has more than 50 papers in national and international journals and has published or edited collected papers of Professor N. Krishnannair. One of my happy moment is he secured his postgraduate degree from St. Thomas College, Thrissur, with first rank, and secured his BSc also with third rank. And during the course of MSc, he qualified UGC NET JRF examination. That was a proud moment for me as well as for Dr. Davis Anthony Mundaseri also. Now, today he is talking on statistical modeling with quantile functions. I think last week, Dr. Shankaran handled this same topic. So today, Professor Sunoj is talking on this. I think he can contribute a lot on this topic. So without much time, I'm not wasting his time. So I'm welcoming Dr. S.M. Sunoj for handling this session. Welcome, Sunoj.
Thank you, Jensen sir. Am I audible?
Yes, sir.
Yes.
Okay. I'm really happy that my two teachers are sitting, even if it is it's a virtual type event. So happy, and in fact, 2 weeks back only, I presented a talk at the St. Thomas College. That time too, Jensen sir was the chairman. He was chairing the session. And in fact, as he mentioned, this particular conference, I'm very much interested just because it's very difficult to attend more conferences in a month's time. So, but I assured him maybe a month back. So if you conduct a program at your college, I'll be one of the speakers that I'm assuring. So today, in that sense, I'm very much happy that he also invited me for this conference. He was a teacher and in fact a motivator for my career. In fact, he taught both Jensen sir and Mundaseri sir, Davis sir. They taught to our batch in both BSc and MSc classes. And it was a very nice time. And as a teacher, as a researcher, he motivated me a lot. In fact, he could not contribute much as a researcher, but as a teacher, I'm sure he proved, greatly, not only at the St. Thomas College he worked earlier, and but at the Christ College, I know he is almost completing 25 or 30 years of service. So this particular talk is dedication, a simple dedication to his memory. In fact, as a teacher, it's honor for me to present a talk at this juncture and this national webinar. So the topic, in fact, we have different research papers. We are working in different areas. And, so since it's being the target audience is being more of students, PG students. So I thought of presenting a more general talk. Of course, we have contributed some papers in this regard, but we are not discussing, I'm not mentioning or discussing much on that part, but this will give you a overview of the topic, statistical modeling using quantile function. So nowadays, many researchers are applying this tool in both modeling and analysis. So hope this will give you, some of you will give you some light on this area. So let me begin with my talk. Can you see my slide?
It's coming. Oh, yeah, it's okay, sir.
Okay. So, as mentioned, this talk is in honor of Professor Davis Muntasiri, my HOD, Department of Statistics, Christ College, Iringalakod. To begin with, a probability distribution can be specified either in terms of distribution function or by the quantile function. The distribution function approach, people are much familiar because most of our discussion is purely based on the distribution function approach. And some of the results we have actually used knowingly or unknowingly using the quantile function. Both convey the same information about the distribution, but with the different interpretations. The concepts and methodologies based on distribution functions are traditionally employed in most forms of statistical theory and practice. Quantile-based studies were carried out mostly when the traditional approach fails to provide results of desired quality. So we will discuss on that part in the coming slides. So why we are interested in this approach. So because in many situations, this traditional distribution function approach fails to apply, and this can be taken as an alternative, and not only an alternative, this can be taken as an effective alternative to model analysis real-time data. So quantile functions have several interesting results or interesting properties that are not shared by distributions. So that is one important aspect. So even if both these approaches convey the same kind of information, but some of the properties quantile function possess that are not shared by the distribution functions. The distribution function approach do not have these properties. So this will be more handy in certain situations that we will see. Quantile-based lifetime data analysis provide an alternative methodology. So primarily, this can be taken as an alternative methodology, and this can also be used as an efficient alternative, so that we will discuss. Now, some historical remarks. Historically, many facts about the use of quantiles in data analysis were known even before the 19th century. So actually, Quetelet in 1846 initiated the use of quantiles in statistical analysis in the form of interquartile range. I think all of you are familiar with the interquartile range, because in the degree level itself, once we study the measures of central tendencies and measures of dispersions, we are studying the different type of quartiles and percentiles. So interquartile is interquartile range is taken as a measure. Now Galton in 1822 to 1911, who actually initiated the ordering of observations along with the concepts of median, quartiles, and interquartile range. But Hastings et al. 1947, who introduced the Tukey lambda distributions using the quantile function, that actually led a major development in the use of quantile function in modeling. So we'll be discussing about this Tukey lambda distributions. That is actually a good model for representing some of the reliability aspects compared to any other models, the existing models. And later, the Poisson, in his seminal paper, emphasized the description of a distribution in terms of the quantile function and its role in data modeling. So this paper is a very interesting paper. This covers gives us many ideas with regard to the quantile functions and how the empirical quantile function is defined, etc., are all discussed in this paper. So that is why this is considered as a seminal paper in the context of quantile functions. Now, outlays have a significant effect on the estimates so derived. For example, distribution methods such as least squares, method of maximum likelihood, and matching moments, generally give the sample mean as an estimate of the population mean, whose value is changing significantly in the presence of outlying observations. So outlays, the presence of the outlays often makes a noise in the estimates because it controls the whole procedure, and in many occasions these outlying observations, because of this the existence of the outliers, the standard estimates or estimators may not be efficient. Okay, so asymptotic efficiency of the sample moments is rather poor for heavy-tailed distributions, since the asymptotic variances are mainly in terms of higher order moments and that tend to be large. Okay, so in reliability analysis, a single long-term survivor can have a marked effect on the mean life, especially in the case of heavy-tailed models, which are not uncommon. So in all such cases, the standard methodology may fail, and these quantile-based estimates are generally found to be more precise and robust against outlays. So this is one of the advantages of using this quantile-based analysis. So the quantile-based estimators are more efficient in this sense, because this in the presence of outliers, rather than using this traditional method of estimators, using the traditional method, this quantile estimates that will serve as an efficient estimator. Another advantage in choosing quantiles is that in live testing experiments, one need not wait until the failure of all items on tested, but only a percentage of them for proposing useful estimates. Thus, there is a case for adopting quantile functions as models of lifetime and base their analysis with the aid of functions derived from them. In lifetime life testing experiments, the quantiles, you don't need all the observations, because with the knowledge of few, it is possible to explain more. So that is an advantage of this quantile approach. There are certain distributions which do not have a tractable distribution function, but a closed form of the quantile function is available. So this is an interesting part. And many of our study, we found this is a very useful property, this quantile function possesses, because certain lifetime data, it is actually or virtually impossible to model using the standard models. In many cases, the quantile models are often more appropriate to model it. Okay, so there are certain distributions. The quantile functions are existing. We have closed form expression for quantile functions, but no closed form expression for the distribution functions. We will encounter some of these models in the coming slides. For recent references, we refer to Gilchrist 2000 and Nair et al. 2013. So the whole discussion is actually prepared based on both these textbooks, Gilchrist and Nair et al. Because Gilchrist book is a fundamental guide to this quantile functions, and later in recently in 2013, Nair, Shankaran, and Balakrishnan. So they have a book on quantile-based reliability analysis. Actually, this book explains more on the reliability side of or reliability modeling and analysis using quantile functions. So most of the results included in the latest book or the later one are basically taken from the research papers published recently in 2030 and just before that. Now, how we define quantile functions? Let x be a real-valued function, a real-valued continuous random variable with a distribution function capital F, which is continuous from the right. Then the quantile function Qu of x is defined as Qu is F inverse U. It is simply the inverse function of the cumulative distribution function. So it is an infimum of x such that f of x greater than or equal to u and u lies between 0 and 1. The definition says that for given probability value u, we are looking for some x that results in fx retains value greater than or equal to u. Since there could be multiple values of x, so that you can expect multiple values for x for f of x greater than or equal to 0. We take the smallest x, and not every function has inverse. It has to assign for each input value exactly one output. However, f of x is continuous and non-decreasing or monotonically increasing. Now, this is the plot of the quantile function. You can easily find that, see that the quantile function. The quantile function is denoted by the blue arrow and the red arrow, the CDF. So both acts complement. Okay. So here from the y-axis, which is in fact the cumulative distribution function, you'll get the distribution function, whereas corresponding to this f of x, for a specified value of this f of x is being a probability, it always lies between 0 and 1. You can find the corresponding x value, which is in fact the f inverse u. So this is now let us move to explaining the use of this quantile function using some standard distributions, and we then move to some unique models, which are some models which are unique to the quantile setup. Okay, suppose x is exponential with a distribution function capital F of x equal to 1 minus e raised to minus lambda x, lambda greater than 0 and 0 less than x less than infinite. Then the quantile function is given by minus 1 by lambda log of 1 minus u. Suppose x is a standard Gumbel, which is also known as the extreme value type 1 distribution, with a distribution function exponent of minus x, minus infinity less than x less than infinite. So it can be easily inverted. The quantile function for Gumbel distribution is QU is minus log of minus log. It is a typo, minus log of U. Okay, so in this for these type of models, it is not at all difficult to find the quantile function, but in certain cases it will be a little difficult to get the quantile form of the distributions. These are some of the this table explained or give you some standard models and the corresponding quantile functions. Here you can see that the models like exponential, Weibull, Pareto 2, recycled beta, half logistic, power distribution, Pareto 1 distribution, bar type 12 distribution. So, and you look at the last column here, you have the quantile functions, and the second column giving you the form of the distribution function. So in this table, we are considering all the distribution that has closed form distribution as well as the quantile function. Okay, Gompert's distribution is well known, and its quantile function is given in the last column. Then Greenwich distribution, Cusp distribution, logistic exponential distribution. Then another distribution introduced by Dimitraka Paulo et al. Log Weibull distributions, modified Weibull, exponential power. So there are plenty of distributions commonly used, and these are the list of distributions and the corresponding quantile functions, and that include the generalized Pareto, inverse Weibull, extended Weibull, generalized exponential, exponentiated Weibull, generalized Weibull, then exponential geometric, and there are many such distributions available in literature. And in fact, both Gilchrist's book and even in fact in the book by the Nair et al., they have listed almost all the distributions available in literature and its corresponding quantile functions, and that is also computed and listed there. Okay. Now, from the definition, we have, in fact, QU is defined. QU is nothing but the inverse of the distribution function. Now, if fx is a probability density function of the random variable x, then FQU is called the density quantile function. The derivative of QU is known as the quantile density function of x. Now, from this identity, QU equal to F inverse U, and it is FQU equal to U, and differentiating, it will result to equation number 2. This is an identity connecting the quantile density function and the density quantile function. Okay, QU into F of QU equal to 1, the product. And looking into the properties, and you will see many properties which are actually complement of the distribution function. QU is a non-decreasing on 0, 1 with QFX less than or equal to x for all x lies between minus infinity to plus infinity. FQU is greater than or equal to U, then QU is continuous from the left, which is actually the complement or the complement of the property of the distribution function. Distribution function is right continuous, whereas the quantile function is left continuous. QU plus is infimum of x such that fx is greater than u, so that QU has limits from above. So that is also possible. Then gems of f of x are flat points of QU and vice versa. If U is uniform, then x equal to QU has a distribution function f of x. Now, another interesting property is if Tx is non-decreasing, then TQU is a quantile function. So if you take a transformation Tx, which is a non-decreasing transformation, then TQU is a quantile function, which is known as the Q transformation. On the other hand, if the transformation Tx is non-increasing, then TQ of 1 minus U is also a quantile function. We will show the use of these type of properties in the later slides. Then the sum of two quantile functions, Q1 and Q2 are, if they are two quantile functions, then the sum of the two quantile functions is again a quantile function. Product of two quantile function is a quantile function. Actually, product of two positive quantile function is again a quantile function. 1 by x has a quantile function, 1 divided by q of 1 minus u. So with this, these are the properties which are not possessed by the distribution function approach. So, and this will serve as a interesting tool or a simple tool to construct more and more models based on the availability of some quantile functions. So suppose you have two quantile functions, and you can take the sum of the two quantile functions, and that results another quantile function. And the only thing is you need to see that that quantile function is also satisfying the properties listed here. Okay, the quantile function of minus x is minus of q of 1 minus u. This is known as a reflection property of the quantile function. Then the sum of two quantile density function is again a quantile density function. This is also a unique property quantile approach possesses, because in the distribution functionist approach there is no such property. If you sum the two distribution functions, probability density function, that is not necessarily a probability density function. Okay, on the other hand, here in quantile density approach or quantile approach, the sum of both quantile function as well as the quantile density function, that results another quantile function or quantile density function. Now the quantile function of the residual random variable x minus t, so that is given by q1u, and so all these things can be, so in this sense, this approach works as a alternate approach, and apart from that, this also provides some interesting and novel properties that are not shared by the distribution function approach. Okay. Now let me go to some of these properties which we have already explained through some examples, and this will give you more clarity on what do you mean by these properties. Okay. Suppose a set of data is obtained from the unit exponential and a minus sign put in front of each observation. You have a data obtained from a unit exponential distribution, and you also put a minus sign on each data, so that the consequent distribution is called the reversed or reflected exponential distribution. So in short, from the data, now you have two data sets. One is the data itself, and another is the data which is the minus sign of the given data, which, so since the given data follows exponential unit exponential distribution, this transformed data is that is a minus sign of the given set of data, that will be reversed or reflected exponential distribution. And we know that for the exponential distribution, this quantile function is given by q1u is for the unit exponential. If you have a parameter, say lambda, then it will be minus 1 by lambda log 1 minus u. Since it being a unit exponential, it reduces to minus log of 1 minus u. Now, I will show you the figure, and before that, the pth quantile for the reflected or reversed exponential is a minus of the 1 minus u quantile of the ordinary exponential, that we will see through the figure which is shown in the next slide. Okay. Thus, the quantile function of the reflected exponential is q2, if I denote it by q2u, which is log of u. So minus of log of 1 minus u is replaced by u, and minus sign is then minus of minus. So it is log of u. So for u equal to 0, this is minus in front, and p equal to 1, it is 0 as required. That means it satisfies the property of the quantile function. Okay. This is the density function. Okay, density function of the density function of the reflected exponential. just a mirror image of the exponential distribution. And so if I plot together both the exponential and reflected exponential in a figure, this would be the case. Okay, you'll see that the one distribution, one curve is exactly the mirror or the reflection of the other. Okay, so one represents the exponential distribution, and the other, the curve below the in the negative quadrant, and that is in fact the reflected exponential distribution. And you can see that this reflected exponential is simply the reflected image of the unit exponential drawn in the positive quadrant. Okay, so that is about the shape of these two distributions. Now, suppose the quantile functions of the exponential and the reflected exponentials are, these two models are added together. So I'm making use of one of the property, as mentioned, if you add two quantile functions, the resultant function is again a quantile function. So I denote the resulting quantile function by Q3. So Q3 is Q1 plus Q2. So simply add the quantile functions here. It is in fact log of U divided by 1 minus U. So this is in fact another, this is in fact the quantile function of another non-distribution, which is nothing but the lowest distribution. So it will be seen that the center line obtaining the addition, obtained by addition, is symmetrical about the value x equal to 0, which occurs at U equal to 0.5, and therefore it is a median. Okay, and it is also evident that in the tails of the shape is that of the corresponding exponential or reflected exponential. This model is called logistic distribution. So log of U divided by 1 minus U is a quantile function of logistic distribution. So by adding, so that is a summary, by adding an exponential unit exponential distribution and a reflected exponential distribution, you are getting another quantile function, which is nothing but the quantile function of a logistic distribution. Okay, so now you look at how the logistic distribution is obtained. So this consists of the three models. So this is a plot containing the three models together. One, the upper quadrant, that is the exponential distribution, and in the negative quadrant you have the we have the reflected exponential, and connecting the two curve, and you are getting that bolded line that actually indicates the lowest distribution. That is the quantile function corresponding to logarithm of U divided by 1 minus U. Now the figure below shows the addition of exponential hello.
Okay, it's okay. I'm continuing.
Some disturbances. Okay. So, am I audible?
Yeah, you're audible. Okay.
Okay. So the figure below shows the addition operation for the quantile density function. So the previous figure actually that showed the quantile functions of the three models. Now this actually depicts the quantile density function plot. Okay, and the quantile density function plot actually giving us a bathtub shaped curve. Okay, this is actually obtained as by the addition of two quantile functions. Now looking into the when you draw the density plot, the actual probability density plot corresponding to these two quantile models, we obtain this particular curve, which is nothing but the curve of the probability density function of the lowest distribution. You know, the lowest distribution ranges from minus infinity to plus infinity, and the lowest distribution is more thicker than the normal curve. So as the derivative of a sum is the sum of the derivative, the addition of two quantile functions must lead to the addition of quantile density function. So this was one of the another property which I mentioned, the adding two quantile density function yield another quantile density function. So this particular figure is an example to that. So here we are getting the quantile, we are adding two quantile density functions, and added together, we are getting a quantile density function again, and that is in fact the quantile density function of the quantile density function is nothing but which is connected to the probability density function of the logistic distribution. Now, some more interesting property one can think of. So suppose a set of data has exponential looking tails, but is much flatter at the peak than the logistic distribution. Okay, so the uniform is totally flat distribution. So consider modeling the distribution by adding. So we want our data. Actually, when we draw the data, this data shows an exponential looking tails, but is much flatter at the peak than the logistic distribution. So it may not be appropriate to model that data using a logistic distribution alone. So here the interest is whether it is possible to derive a new model that suit best to the given data. Okay, so that type of modification can be applied. So here modeling the distribution by adding a multiple k of the uniform to the logistic. So what we do here, here we have a quantile function log of u divided by 1 minus u, which is a quantile function of logistic distribution, and to incorporate or into address this flatter tail than the logistic. What we do, we have added a constant multiple of u and the shape of PDF for this model, and can be seen that it suitably combines the properties of the uniform. So this KU is what? KU is nothing but the quantile function of the uniform. Okay. So it combines. Now we have actually the first part is the combination or the sum of the two quantile functions, exponential and reflected exponential. Now we have added one more model which is uniform. Okay, so and through this process, what we achieve here is we are having a resulting, or the resulting model is fit more to the given observation, because it is the tail of the distribution is much flatter than the tail of the logistic distribution. Okay, so now so this QU giving us a flattened logistic shape. Okay, the median is k by 2, indicating the shift in position of the distribution due to the added uniform distribution. So this is what happened. Okay, so now we have added the uniform distribution, and this is a plot. So the lowest distribution has been shifted. Actually, the lowest distribution, the ordinate was at x equal to 0. Now this has been shifted due to the adding of the constant multiple of the uniform quantile. So, and this will be the resulting shape of the distribution, and this we can call it as uniform logistic. Okay. Now another interesting property one can think of. In the first example, the exponential and reflected exponential distributions were combined. This was done by equal weighting for the two. Okay, so we have given equal weight to both the distributions. That is why we simply sum the two quantile function of the exponential and the quantile function of the reflected exponential. Now, suppose we want to have more flexibility in your data. So in that case, you can think of giving some weight to the each of these quantiles, so that you will get a more flexible quantile, and that may address the required form of the data. So the PDF for the model defined by the quantile function will be QU equal to 0.8 times minus of log minus log 1 minus u, which is the exponential distribution quantile function of the exponential distribution. So we give more weight to exponential side and less weight to the reflected exponential side. Okay, so this distribution is now skewed to the right. So in the former case, it was a logistic distribution, and the logistic distribution is a symmetric distribution. But because of this weighting, the resulting model becomes a skewed distribution, and this skewness can be adjusted by changing the weights you applied on these two quantiles. since here we are getting a distribution which is skewed to the right, since more weight is given to the exponential term than the reflected exponential. This is called skew logistic distribution, and this is how the new models are generated by taking quantile functions. The general basic form of the distribution can be written as Q equal to W times minus log of 1 minus U plus 1 minus W of log U. Now, now looking to another property, if a quantile function is positive, it can be multiplied by another positive quantile function to obtain a new distribution. And this is one of the property I have already listed. And this property is a unique property to the quantile approach, and that are not shared by the distribution function approach. So, for example, the two positive distributions, say the uniform distribution and Pareto 1 distribution. You know, the Pareto 1 distribution with a long tail to the right, you know, this Pareto distribution is mainly used in income studies because of this long tail to the right. It has a quantile function Q1U given here, and the distribution range is 1 to infinite. And for the uniform quantile function, you know, Q2U is U, and here we are taking the product of the two quantile functions, uniform and Pareto 1, you are getting another quantile function which is denoted by Q3U. And so uniform distribution is a special case of the power distribution defined by the quantile function U raised to alpha. Okay, for uniform distribution, the quantile function is U, because, and for the power distribution, it is U raised to alpha for alpha greater than 0. So uniform is a particular case of the power distribution. So here, in fact, we can think of taking product of power distribution and Pareto distribution, and the resulting distribution, we call it as power Pareto distribution. So this, the Q3U is in fact a particular case of the power Pareto distribution with the alpha equal to 1. Right? And another property I have mentioned that if you make some transformation, if Tx is a non-decreasing function, then TQU is again a quantile function. Okay, so let us take the consider an example. The underlying distribution is Pareto 2, and its quantile function is given here. And suppose I take a transformation x raised to beta. Okay, x raised to beta, you know, it is a non-decreasing transformation. And what will be TQU of U? Just plug in wherever x, you plug in QU there, and the resulting distribution is obtained. When TQU equal to y, we have, on solving for y, you have U equal to GY, which is 1 minus 1 plus y raised to 1 by beta divided by alpha all raised to minus e. This is the Burr type dual distribution. Hence, TQU is a quantile function. So, by applying this transformation, you are getting another quantile function, which is again in this case a non-distribution, which is the Burr type dual distribution. Now look at here. Another property we apply here. I take the Pareto 1 distribution instead of the Pareto 2. Here I am taking Pareto 1 distribution and making a transformation Tx equal to 1 by x. 1 by x, you know, it is a non-increasing transformation. So what will be the resulting quantile function? Then we know that T of Q of 1 minus U is another quantile function. And this will be the distribution function of a power distribution. So this is again a quantile function. Now, some of the descriptive measures based in the context of quantile functions are by substituting U equal to 0.5, you'll get the median, and dispersion is measured by the interquartile range. What is interquartile range? It is not nothing new. You're all familiar, which is Q3 minus Q1, and Galton's coefficient of skewness, which is actually explained through the 3 quantiles, Q1, Q2, and Q3, which is given by Q1 plus Q3 minus 2 Q2 divided by Q3 minus Q1. And the kurtosis can be measured using the formula which is given by T is Q of 0.875, like that expression that will give you the kurtosis measure. and mean difference by delta. So all the distributional properties can be explained or can be sought by the quantile functions itself. So you don't need the probability density function to explain these properties. In fact, in the distribution function approach, you need to find the mean, the first 4 row moments, and these first 4 row moments actually giving us the information about this skewness and kurtosis. But you look at here, in explaining the skewness of a distribution or kurtosis of a distribution, you don't need anything of this moments required, but instead it can be explained purely based on the quantile functions. Okay. Now, how will you, what will be the empirical quantile functions? This empirical quantile function is actually explained. This is suggested by Poisson in that seminal paper, 1979 paper, which is, I think, in the American Statistician book, Statistician journal. It appeared in that journal, and this journal provides more results in this regard. They also introduced the conditional quantile functions, etc. Okay, so the empirical quantile function is given by this quantile function is QNU is the XRN. So it is nothing but it is the rth order statistic. Okay, and the second one is a modified version of the first statistic. The first statistic is a rth order statistic, and the second one is a modified version of the same, and which was proposed later. I think in the Poisson paper itself they have given this modified version. So before that it published the modified version, which is also called the smooth version. It's something like a kernel type function, and but empirical method, because the empirical quantile density function is QNU. Small QU is a quantile density function, and the empirical quantile function is n times the difference, which is nothing but the spacing. So based on the spacings, the spacing will giving you the difference between the 2 adjacent order statistics give us the quantile density function. Okay, now this the distribution, for the rth order statistic, the distribution function, and the quantile function of the rth order statistic is given in the last line. I'm skipping that part. And what are the methods, general methods applied in the case of quantile approach? So instead of the standard moments, regular moments used in the distribution function approach, in the quantile approach, we use the method of L moments. L moments are basically the linear functions of the order statistics. So based on the order statistics, one can find the construct the L moments, and through the L moments we can estimate the parameters of the models. So what we do, equating sample L moments to population L moments. This is the same principle which we applied in the case of method of moments. So method of moments, what we do, sample moments is equated to the population moments. So here in L moments, the same principle is applied. Sample L moments is equating to population L moments, but L moments are basically linear combinations of the order statistics. And method of distributional least squares, you look at here the standard least square procedure, you are all familiar. So instead here we take a distributional method of distributional least squares. Here the sum of the different squares of the difference between order statistics and the estimates of mean are minimizing, and through which we will find the estimates. Okay, so that is the method of distributional least squares. And method of maximum likelihood is also used by constructing the likelihood function, and the likelihood function to be maximized, and through which we can determine we can estimate the parameter theta. And now what is L moment? Because this is more popularly considered in the quantile approach. The standard practice to summarize a probability distribution or an observed data set is through its moments or cumulants. It is also common when fitting a parametric distribution to a data set to estimate the parameters by equating the sample moments to those of the fitted distribution. Moment-based methods, although long established in statistics, are not always satisfactory. Why? It is sometimes difficult to assess exactly what information about the shape of a distribution is conveyed by its moments of third and higher order. The numerical values of the sample moments, particularly when the sample is small, can be very different from those of the probability distribution from which the sample was drawn. And the estimated parameters of the distributions fitted by the method of moments are often marked less accurate than those obtainable by other estimation procedures such as method of maximum likelihood. So with these comments, so we introduce the L moments, because L moments is an alternate approach, is based on the quantiles, which we call, these are analogous to the conventional moments, but can be estimated by linear combinations of order statistics, as I have already mentioned. L moments have the theoretical advantages over conventional moments of being able to characterize a wide range of distributions, and when estimated from a sample, of being more robust to the presence of outliers in data. So this is one of the interesting property in by using this L moments, because as mentioned, this is more robust against outliers. Experience also shows that compared with the conventional moments, L moments are less subject to bias in estimation and approximate their asymptotic normal distribution more closely in finite samples. Parameter estimates obtained from L moments are sometimes more accurate in small samples than even in the maximum likelihood estimation. So in certain occasions, this works more efficiently than the traditional method of estimation of parameters. And often this has been being used because of the reason that, as mentioned, this is robust against outliers. How L moments are defined, as mentioned, this is the linear combination of the order statistics, and this is a definition of the L moments. And another moment which are associated to the L moment is, or commonly used by many researchers, is the probability weighted moment. Okay, PWM. PWM and L moments are interrelated. Actually, there is a famous two papers by Hosking on this L moments and probability weighted moments. So probability weighted moments can be expressed as a linear combination of L moments. So L moments are basically linear combinations of the order statistics. Now probability weighted moments are linear combinations of L moments. So the procedure is based on PWM and L moments are equivalent. So which one is more handy, we can use it. And because both yield the same result, and also if one moment available, the other moments can also be obtained quite easily through a one-to-one relationship or a standard identity derived. So these are the expressions for the L moments. This giving you the rth L moment and the respective first four L moments, okay, which are denoted by lambda 1, lambda 2, lambda 3, and lambda 4. And L moments exist whenever. So the condition for the existence of the L moments is simple, because it is less restrictive in the sense that you need to have only one condition, which is expectation of X is finite. So even with the existence of the first moment, the L moment will exist. All the L moments exist. So that is the advantage over the standard regular moments approach. Okay, the first and the second L moments provide measures of location. So similar to the standard methods we applied in the distribution approach, here the L moments serves equally to represent or to obtain the distributional properties of a population, because through the first and second L moment giving you the measures of location as well as the spread. And from the third L moment, we can construct a L coefficient of skewness. Okay, you know the coefficient of skewness in the distribution approach is mu3 divided by mu2 square. So similarly, here in tau 3 serve as the L coefficient of skewness, and L coefficient of kurtosis is denoted by tau 4, and tau 4 is lambda 4 divided by lambda 2. And I have already mentioned that the two approaches, PWM and L moments, are equivalent in the sense that now we have the list of a relationship. You know, this theta 100 is nothing but the first L moment. Theta 100 is a notation for the probability weighted moment, and it is nothing but the first L moment. And similarly, you can construct the second, third, and fourth probability weighted moment, and from that will giving us also the L moments, respective L moments. So this is the interrelationship. And method of percentiles is also used as a method of quantiles. Okay, the pth percentile of population described by the distribution QP is simply QPI, where 100 into P8 is a suitable percentage, and the corresponding sample percentage in Q quantile can be obtained from the data. So sometimes when you have taking say 10th percentile, 50th percentile, in our research papers also we have used this method of percentiles to estimate the parameters. For example, suppose the model contains 3 parameters. So in that case, we can think of using 3 percentiles, say 10th percentile or 20th percentile, 50th percentile, and 80th percentage, or 10th percentile, 50th percentile, and 90th percentile, because to get an equal interval of the percentile. So it is not necessary that, but otherwise it will not explain the tail end behavior of the population. So that is why we have equally distributed percentiles are taken to estimate the parameters. So method of percentile is also a commonly used method to estimate the parameters in the quantile approach. Okay, you might have noted in most of the softwares it will give you the quantile plots. So
Excuse me, Dr. Sunoj, can you
yes,
finish by another?
I will finish it by 1 or 2 slides. Okay. So I know the time. Okay. Suppose QU is a suitable model, then first we order the set of observations x1, x2, etc., xn, and PR r equal to 1 to n are the corresponding probabilities. Then Q plot is the plot of points QPR and XR. Okay, so the plot will give for a good model an approximately straight line, since the model gives P quantiles, XP as a function of P, that is XP equal to QP. And that is why in a quantile plot, we look for the 45-degree line, and if the points are plotted or lying around this diagonal line, we say that it's a good model. So that is a method of evaluating the goodness of a model using the QQ plot, similar to the PP plot used in the distribution function approach. So even if we are not that much familiar with the QQ plot, but many people or many students use this quantile plot along with the PP plots using the available softwares. So this is what why this QQ plot is important and how it is obtained. Now, so I think I stop here, because now the next section onwards we are entering to the reliability based methods. So I think I can stop here. And if you have any queries, and there are many slides I can explain, but it will be slightly deviated to the quantile based reliability analysis. So that also many quantile models would be discussed in that section. As mentioned, the Tukey lambda distribution, generalized lambda distributions, then Govindarajulu distributions, then power factor distribution. All these models will be discussed in detail in this in that slides or in those slides. So I'm skipping that part for the time being because I have a time restriction. So thank you very much for your patient hearing. So thank you.
Okay, any queries or suggestions? Anything you want to supplement?
Hello, Sunoj. Hello, Sunoj, I'm audible?
Yes,
Yeah, yeah.
yes, sir. Yes, sir. Yes, sir.
Very much
Yes,
audible.
Sunoj, very much thank you for your nice presentation on this topic of quantile. Very informative and also including all the basics. I have a very small clarification regarding the quantile function. We are depending on the distribution function capital F of x.
Yes, yes.
In literature, is there anything in parallel with F bar? That is in F bar. Is it analogous to the other side?
Because F bar is basically the complement of the distribution function. So F bar in reliability setup, instead of the infimum, we need to use the supremum value. That's all.
That's all. Okay, so the things results are always analogous to the results we get.
But people are more applying this quantile type. Even in the reliability setup, some of the papers I have seen it using this that quantile type.
Even in certain functions like distribution functions of exponential, variable, etc. More cute function is F bar.
Server function. But here this quantile function is much handy because it it is not a problem at all in the quantile approach.
Okay, any more? Okay, if there is nothing, just I want to mention my personal vote of thanks. Official vote of thanks will come after this. On behalf of all present here, thank you, Dr. Sunoj, Professor of Statistics, for a nice presentation on statistical modeling with quantile function. You have given a very good insight to us on quantile function and its application. Thank you, Dr. Sunoj. I express my big thanks to Dr. Sister K.D. Mariama. Don't say K.D. Mariama, Mariam. Dr. Sister Mariama K.D., I think. And her team for organizing a 5-day webinar, RISMA, Recent Innovations in Statistical Methods and Applications, as a tribute to Dr. Davis Anthony Mundaseri. As all of us know, Dr. Davis Anthony Mundaseri has done a marvelous job in Christ College. He served as IQAC coordinator, and now he is serving as controller of examinations of Christ College, apart from his regular duties such as associate professor and head of Department of Statistics in Christ College and research guide in St. Thomas College, Autonomous Thrissur. Really, you have completed all your duties in a wonderful manner, and wish you an energetic and peaceful life after your retirement. Thank you. Thank you, Dr. Davis, as well as Dr. S.M. Sunoj.
Thank you, sir. Thank you, Dr.
So I must include, actually, I also wish to thank the coordinator, the main coordinator, Sister Josephine. Okay. So I missed to mention that. Okay, thank you very much. Because she contacted me several times for this program.
Okay.
Thank you, Jensen sir. Now I call upon Ms. Sridevi PN, Assistant Professor, Christ College Autonomous, Irinyalakuda, to deliver vote of thanks. Over to you, ma'am.
Thank you, Miss. Am I audible?
Yes,
yes. Yes.
Good evening, all. On behalf of Christ College Autonomous and Department of Statistics and everyone who is gathered in this platform, I would like to extend my gratitude to Dr. S.M. Sunoj sir for an enlightening session on the topic statistical modeling with quantile function. The point where Sunoj sir told us about this topic was really informative and will definitely help us in our studies and future. Once again, I would like to thank Dr. S.M. Sunoj sir for taking out time from their busy schedule and enlightening us with the knowledge. Thank you. Thank you so much, sir.
Thank you. Thank you, Jensen sir. Thank you, Davis sir. So once again, thank you one and all.
We can see you.
Thank you, Sridevi. Dear participants, kindly note that feedback form link is available in Zoom's chat box. Once again, thank you all for participating in today's webinar and hope to see you all again on 3rd March 2021 at 2 p.m. Thank you all.